Recording. Right, so, oh, and I need to make this bigger. There we go. All right, so let's start. So we finished last time talking about the, what did we finish last time talking about? I just had my notes. Well, we were talking about rotational motion and rotational energy. We were also talking about rolling without slipping, and so we're going to continue talking about that. But first we need to talk about, first we need to do some discussion about kinetic energy again. So we're going to talk about total kinetic energy. And it's kind of exactly as it sounds. It's just the sum total of the translational kinetic energy and the rotational kinetic energy. Now, the important point is that these aren't really different things. They're just different ways of writing the same quantity. The idea is the total kinetic energy of a system is you break the system up into infinitesimally small chunks, and then you find the translational kinetic energy of each of those chunks and then add them together. However, we can get around some of the particular nastiness of those calculations by breaking it up into translational kinetic energy, that is kinetic energy associated with translational motion, and rotational kinetic energy, which is kinetic energy associated with the body itself rotating or moving with respect to other parts of the body. So let me do an example. Let's consider an object that is both moving linearly Translational kinetic energy is the energy of motion, is the energy associated with motion in a linear manner. It's the energy that's not associated with the rotation about the center of mass. It's the energy associated with the center of mass itself moving locations, both moving linearly, and it's rotating. So we're going to consider a more complicated case, right? So let's look at this example. So we have two rocks connected by a string, and we're going to ignore gravity, or not ignore it, but and we're just going to assume that they're floating out in space or whatever. There's no gravity here. So the picture is you have one rock, maybe of mass 2m, connected by a string to a rock of mass m. And it's spinning. They're twirling through the air. They're orbiting each other. Let's say this distance here is L. And also, on top of that, the whole system is moving. So they're spinning around, but the whole thing is moving to the right. So let's say that the center of mass is moving to the right. Now let's just think about this for a moment. Where should the center of mass be? Well, there's twice as much mass on top than there is on bottom. So we would expect that the center of mass should be twice as close to the larger mass than it is to the smaller mass. And in fact, that's exactly correct. The center of mass is right about here. It is, this distance would be L over 3. This distance would be 2L over 3. And you can double check by doing the center of mass calculation if you want. But that is the center of mass. Now, this is just a snapshot in time, remember. The whole thing is rotating, but it's rotating about its center of mass. So the center of mass is only moving to the right. Now, we can ask the question, what is the total kinetic energy of the system? Now, there are two ways we could compute this. And I'm going to show you how they're equivalent. So what we're going to do is we're first just going to compute the kinetic energy of each of the rocks as we normally would. We do 1/2 mv squared for each of the rocks and then add them together. So the kinetic energy of the top rock is just 1/2 times twice the mass. And I'm going to find the kinetic energy in the configuration it's in. The kinetic energy won't change with time, but sometimes it's easier to calculate depending on the orientation of your objects, especially because they're rotating. So at this instant in time, as I've drawn, the kinetic energy of the top rock is 1/2 times 2m times the speed of the top rock squared. Now the top rock is moving at a different speed from its center of mass, because not only is the center of mass moving to the right, the whole system's also rotating. So the top rock has some additional speed to the right. So in particular, this would be 1/2 times 2m times the center of mass speed plus the distance from the center of mass to the top rock, so I'm going to call that r top, times omega, quantity squared. Now, the reason this term shows up is because that is the translational speed it has associated with its rotation, right? Remember that the translational speed associated with rotation is just r times omega, where omega is the angular speed. You can think of this like on a carousel. How do you find the speed that the object is traveling at? The translational speed, if you know its rotational speed, what you do is you multiply the distance times the rotational speed, and you can prove that by looking at how the arc length changes with time. But regardless, this is what we see, and so we can expand, and we get 1/2 times 2m times vcm squared plus 2 r top omega vcm. I'm just foiling out, plus r top squared omega squared, and then we can do the same thing for the bottom rock. So we would find that this is 1/2 m v bottom squared. And again, the bottom rock is actually moving more slowly than the center of mass velocity. And the reason for that, or than the center of mass speed, and the reason for that is because at this instant in time, the bottom rock is traveling, or the rotation forces the bottom rock to have some extra speed to the left. So this would be 1/2 m times vcm minus r bottom times omega, quantity squared. And then we can do the same sort of expansion. We get 1/2 m vcm squared minus 2r bot omega vcm plus r bot squared omega squared. Now, like I mentioned above, the distance from the center of mass to the top rock is L/3, and the distance from the center of mass to the bottom rock is 2L/3. And that's just because the bottom rock has less mass than the top rock. So we would expect that the total kinetic energy would just be the sum of the two. Right? That's just like kinetic energy just adds. So what I'm going to do is I'm actually going to split up these terms. I'm going to split up these terms. I'm going to split, when I do this addition, I'm going to split up the middle terms from each of them and write them separately. So what we're left with is we get 1/2 times 2m times vcm squared plus L/3 squared omega squared. So that's the first two terms here, right? Plus 2m times L/3 times omega vcm. That's this middle term. I just canceled out the 1/2 and the 2. And so we're just left with 2m times L/3 times omega vcm. And then I'm going to do the bottom terms. This is 1/2 times, and I'm going to do the same thing, times m times vcm squared plus 2L/3 squared omega squared minus, so that's these first two terms, and then I'm going to subtract off that middle term, minus m times 2L/3 times omega times vcm. Okay, so this is the total kinetic energy. Now we can do some more simplifications, and so we may as well do that. In particular, these two terms cancel. And that's not that, there's a good reason for that, and that's because of what we're about to see happen. Those two terms are basically cross terms, and they should cancel. They're just a result of, well, I mean, you can see why they happen algebraically. But that will happen in general. So why split the velocities? The only reason I did it, it's not because I'm doing anything tricky. It's just to illustrate how these simplifications occur. So what we're left with, we can actually combine the remaining terms, and we get 1/2 times 3m. So combining, I don't need a parenthesis there. Sorry. No, I do need a parenthesis there. Combining these first two terms, we get 1/2 times 3m times vcm squared. And then we combine the last two terms, plus 1/2 times 2/3 ml squared omega squared. Now, just as a note, the moment of inertia of the center of mass of the system is the sum of the moments of inertia of each individual part. And this is just a discrete system, right? We know how to find the moment of inertia of a discrete system. You just do m times r squared for one of the objects plus m times r squared for one of the other objects. So this would just be 2m times L over 3 squared. So that's for the top rock, plus m times 2L over 3 squared, right? So that just works out to be, sorry, one sec. You can do some simplification, and it just gives you 2/3 ml squared. So what we find is that the total kinetic energy of the system, just by finding the speeds, the translational speeds, and ignoring any rotational motion, just by writing the translational speeds, which incorporate some rotation, and then writing out the standard kinetic energy, we find that this is equal to 1/2 times the total mass, because the total mass of the system is 2m plus 1m, times VCm squared, plus 1/2 times the moment of inertia of, about the center of mass times omega squared. And so this term here is the translational kinetic energy. I'll write subscript trans. And this term here is the rotational kinetic energy. And so what we can see is that the total kinetic energy of the system could have been determined a lot more easily. Instead of finding the speed of each rock at a particular point in time, instead we just find the kinetic energy of the center of mass using the total mass as the mass of the kinetic energy. So that would just be 1/2 times the total mass, which is 3m, times VCm squared. And then we find the kinetic energy associated with just the rotation, which would be, you'd find the moment of inertia of the whole system, and you'd multiply that by the angular velocity squared and multiply it by 1/2. And that gives us the same answer. In fact, they're just two separate ways of doing the same calculation. Now, just as an aside, the moment in time that I chose to calculate the energy here didn't actually matter. However, it would have been trickier to do this calculation if for example, we had instead decided to calculate it when it was horizontal, because then the velocities wouldn't directly add or subtract with the center of mass velocity, and it just would have been a lot nastier. We would have gotten the same answer at the end of the day, but it just would have been messier. So the point is calculating the first way, just finding the speeds of each of the parts and then adding up the total kinetic energies, the difficulty of doing that calculation can very much depend on the orientation and the arrangement of the objects that you're calculating with. However, if we had it instead calculated by just finding the translational kinetic energy of the whole system and adding to it the rotational kinetic energy of the whole system, that wouldn't care what orientation this system is in at any given time, because the translational kinetic energy doesn't care about orientation, nor does the rotational kinetic energy. No, not really. This is just the I of 2m, and this is the I of m. And that's just using the original definition of moment of inertia. It's just moment of inertia is m1 times r1 squared plus m2 times r2 squared. That equation is valid whenever you have point masses like we have here. These are assumed to be point masses, of course. Now, that equation is, in fact, the parallel axis theorem is kind of a result of that equation, but we can go into that in office hours if you're interested. Right, okay, so let's keep going. So in some cases, an object rotates about a point fixed in space, not objects. About a point fixed in space. And I will elaborate on this in a minute. But in that case, so the thing to imagine here is perhaps like, again, you tie a rock to a string and you swing it around your head. It's rotating about a fixed point in space. So the center of mass isn't really, or the center of mass is moving, but the point about which the system is rotating is not moving. But regardless, in that case, the total energy is just equal to the rotational kinetic energy about that fixed point. So the rotational kinetic energy, by the way, depends on what point the object, or what point you're calculating the moment of inertia about, right? Because the moment of inertia depends on the axis of where the axis of rotation is. So if you calculated the moment of inertia about one axis, it might be different than if it were about a different axis, even if they have the same angular velocity. So when you talk about the rotational kinetic energy, you actually have to talk about the kinetic energy of rotation, or associated with the rotation about a particular point in space. Now, often we'll either talk about a fixed point, or we will talk about the center of mass. Those are the two most common, but those aren't the only options. But regardless, so this kinetic energy, this rotational kinetic energy about that fixed point, that's equal to 1/2 times the moment of inertia about that fixed point times omega squared, right? The kinetic energy is always 1/2 times whatever the moment of inertia should be for whatever thing you're trying to compute times omega squared. Now, so let's try to understand why. So we're going to assume in this case that the point of interest, the fixed point, is not the center of mass. And the reason for that is because if it were the center of mass, this is a lot more obvious. If the object is just rotating about its own axis, there is no translational kinetic energy. And so in that sense, of course, the total energy would be the rotational energy. The total kinetic energy would be rotational kinetic energy. And in that case, the fixed point would just be the center of mass. So we're going to assume that we're talking about like a rock going around in a circle from like your hand because you're holding onto a string or something. That's a more general case, and it's on its face more complicated. So we're going to assume the fixed point is not at the center of mass, and further we can let's just say that say the fixed point is d units from the center of mass. So maybe the string that we're talking about attached to the rock that we're holding onto is 2 meters long. Then d would be 2 meters. And the reason we need that is just because that will play a role in what the moment of inertia is. So then the center of mass follows a circular path. A circular path of radius d around the fixed point. And I'll draw a picture here. So we have our fixed point here. And then we have our object, whatever it is, and its center of mass, maybe it's in the middle. It doesn't have to be in the middle, but the center of mass is where it is, and this distance here is d. And our object is, say, swinging around. Maybe it's orbiting because of gravity, maybe it's attached to a string, so it's attached. But regardless, it's going around the fixed point. And so in this case, that implies that the center of mass velocity is, and it has some angular velocity omega, is omega times d. Remember that speed and velocity, angular speed and translational speed and angular speed are just related by the distance from the axis of rotation to the object that's moving. This is the same thing as just r omega. I just wrote it as omega d instead. So what then? So the rotational kinetic energy, or the total kinetic energy, if we were to compute it the way we had before, yeah, it is. The total kinetic energy, which naively is just the sum of the translational and the rotational kinetic energy about its center of mass, 1/2 mvcm squared, plus 1/2 ICM omega squared. This is, well, we know what VCM is, right? It's 1/2 m, and VCM is omega d squared plus 1/2 ICM omega squared. And so we can actually factorize this, and we get 1/2 times md squared plus ICM omega squared, right? But the important point is that this is the moment of inertia about the fixed point. And the reason that's the case is that comes from the parallel axis theorem. Parallel axis theorem is that you take your moment of inertia about the center of mass, you add to it m times the distance to the axis of rotation squared, and that's the moment of inertia about that new axis. And so this is just equal to 1/2 times the moment of inertia about that fixed point times omega squared. Omega is always rotational speed. Always true. Now, I would show you a demo, but again, don't really have stuff in person. But the whole point is that, or what we're about to get to, is something called, we are going to proceed, and we're finally going to get to talk about perfect rolling, or rolling without slipping. Because now we can understand how translational velocity and rotational velocity can interact with each other via energy conservation. So let's put this aside for a minute and let's go talk about perfect rolling. So for perfect rolling, any potential energy, think like a disk rolling down a hill, any potential energy can be distributed into either the translational kinetic energy or the rotational kinetic energy, or both. The non-slip condition, this is the fact that it's rolling exactly as much as it's moving. The non-slip condition, which is given by VCM equals R omega, determines how much goes where. And I'm going to illustrate this in a minute. So the whole point is that if you have like a barrel rolling down a hill, right? Because we can assume that the barrel doesn't slip, if the barrel has a really, really small radius, then it has to rotate a whole bunch of times in order to cover a small distance, right? Whereas if the barrel had a really, really large radius, a single rotation is enough to take it very far. So the fact that the translational speed of our rolling object is related to the angular speed basically tells us what the relationship is between angular speed, or what the final relationship is between angular speed and translational speed, and how that how those speeds, in the form of their associated energies, how those quantities are distributed from the potential energy that the object may have initially had. So put into words, the bigger the center of mass moment of inertia is, the larger the fraction of kinetic energy it gets. Of the total kinetic energy. So let's explain this just by doing an example. So we have our triangle, or our inclined plane rather. Maybe this distance here is h. We have our disk. Maybe it's a cylinder, maybe it's a disk, whatever it is. This has radius r. And it starts off at the top at rest. And at the bottom, it will be rolling at some speed, right? We want to find out how fast is it moving, what's its rotational velocity, and so on. So we would use energy conservation here. And again, we're going to do the normal thing where we neglect friction and so on, and drag and all that business. So initial potential energy plus initial kinetic energy. And here, this kinetic energy, when I write KEI, that is the total initial kinetic energy, is equal to the final potential energy plus the final kinetic energy. Now, you guys have hopefully done these types of problems enough that PEI minus PEF, that should be a positive number because it starts off higher in the, or yeah. So you guys have done this enough that you know how to rearrange this. And so we would have MGH on one side, that is the change in potential energy. Potential energy decreased by MGH, and so the kinetic energy will go up by that same amount. Sorry, the kinetic energy will go up by that same amount. It started off at rest, so its initial kinetic energy is 0, so it's just final kinetic energy that we're looking at. So this would be 1/2 mv squared plus 1/2 I omega squared, where this I is this is the moment of inertia about the center of mass. This v is the speed of the center of mass. But when it's obvious what we're talking about, I'm going to drop those subscripts. All right, so we can just do some simplifications now. We have mgh is equal to 1/2 mv squared plus 1/2 I, and now we can do a substitution. We know from the non-slip condition, we know that v cm equals r omega. So in particular, omega is v over r. And so that is, we can rearrange this, we can rearrange this even further and get that, or factor rather, and we get that 1/2, we get that mgh is equal to 1/2 m plus I over r squared times v squared. And so then we can just solve for v. So the speed that the object is rolling down the hill with, or that the cylinder, whatever it is 2 mgr, square root 2 mgr. All I'm doing is I'm just multiplying by 2, dividing by m plus I over r squared, and then I'm multiplying and dividing by r squared, just to simplify. Divided by I plus m r squared. So it's a relatively straightforward calculation, and it relies on the fact that we can substitute in omega equals v over r. And that's that condition, this is a constraint, by the way. That condition is what tells us that the object isn't slipping, and it's what lets us solve this problem to begin with. Because you can imagine that if this inclined plane was really slippery, the object would just slide down the hill. And if it was really rough, the object would roll and slide as it rolls down the hill, and so it would roll more slow, or it would go down the hill more slowly, because some of its energy is captured in this rotational motion. The constraint is the non-slip condition. I dropped an H. That shouldn't be a G. That should, or I need MGH. Good catch. MGHR. There we go. Thank you. Good catch. I'll fix that in my notes before I upload them. Right. So what we find just by, we can just look at this equation. Obviously, if we were on a different planet where G was larger, it would be moving faster when it got to the bottom. Obviously, if H was increased, it would be moving faster. But now the question is what happens if you increase the radius of our barrel? Or what if you change the mass? Well, so it's hard to say, because both the moment of inertia and obviously the mass, both of those depend, or the moment of inertia depends on both the mass and the radius of the object. It depends on it depends on how much mass it has and where that mass is. But what we can say is we can say that if the moment of inertia is large, then v is small. And what that implies is that the translational kinetic energy has less of the total energy. Whereas if I was small, then v would be larger, up to a certain point, of course. You can't just keep decreasing I and make v go up forever. When I is 0, v is some finite number. So we can go even further, and we can actually start talking about what this specific moment of inertia is for various shapes. In fact, for a cylinder of any kind, it turns out that the moment of inertia is proportional, that's what that little fish thing means, is proportional to the mass times the radius of the cylinder squared. So in this case, the wait a minute, something's not right. This should be an r squared up here. Sorry. In this, yeah, because I multiplied and divided by r squared. In this case, we actually see that v is independent of the mass and the radius, which is interesting, right? Like I could have substituted in that. So if I is proportional to mr squared, I could have substituted that I is equal to, say, alpha mr squared, where alpha is just some number, some constant of proportionality. Then we could have canceled out the mr squared on the numerator and the denominator, and v would just not care at all about the mass of the cylinder or the radius. And that kind of makes sense, right? It shouldn't, like, we know that the rate at which things fall doesn't usually depend on the mass. It usually just depends on, like, gravity, and that's it, right? The same applies here. However, what does matter is that depending on how that cylinder has mass distributed in it, the constant of proportionality will be different. So for a hollow cylinder, and this is just something that you could either look up or you can trust me on, this is a hollow cylinder, so like think like a Pringles can. The moment of inertia about its central axis is just equal to mr squared. And for a solid cylinder, what would be an example of a solid cylinder? Well, you guys know what cylinders are. The moment of inertia is 1/2 times mr squared. Yeah, well, no, because it has to be uniformly distributed. The moment of inertia is 1/2 times mr squared. So the only difference between the only difference of the moment of inertia about the solid versus the hollow cylinder is just what this constant of proportionality is. It's either 1 or it's 1/2. And you can imagine that if you have like a cylinder that's less dense in the middle and it gets gradually, or that's dense in the middle and it gets gradually less dense as you go out, that constant of proportionality might be different. But as long as it's cylindrically symmetric, that the mass distribution, it will always be proportional to mr squared. And so you could just plug these in depending on what type of cylinder we're talking about. You could just plug those in there, and you would find what the speed is, and it wouldn't depend at all on the mass or on the size, the radius of the cylinder. So this is how you do rolling without slipping, and there's a problem on the homework that uses material like this, so keep this in mind. Now, we have a lot of tools now, like this rotational motion is really powerful to understand more complicated systems. So we're gonna change gears a little bit, no pun intended, I guess. And we're gonna look at an old assumption we made. We're gonna look at massless pulleys. So in the past, when we've talked about like tension and we have pulleys and we have all sorts of that kind of stuff, we would assume that our pulleys are massless. And the reason we do that is because it makes our calculations easier. However, we don't have to assume that they're massless anymore. Because now we know how to understand rotational motion. So let's work out an example. An illustrative example. So let's say that we have a falling mass which is attached to like a spool of thread or something, which is unwinding. So we have our spool of thread, maybe it's mounted on the wall, right? Has its axis of rotation, has some radius, and the spool of thread has some mass. And one of the threads, or the thread is like pulled off, and it's just attached to a mass. And that mass is falling and unwinding the spool of thread. I'm going to make this lowercase m. Initially, it would be at rest, right? Because right before you drop something, it's at rest. But then at a later time, the mass will fall and it will unravel the spool of thread. Now we're going to assume that the thread itself is massless and that the diameter of the spool doesn't change. That's technically an assumption because thread isn't massless. The diameter would change because you're decreasing the amount of wraps it has on it and so on. But it's a pretty reasonable thing we can ignore because those effects are pretty negligible. So let's say it falls some distance h, right? And it would have some downward speed v. How would we find the speed that our block is falling at? Well, we could use energy conservation again. And by the way, this is another example of a non-slip condition because the rate that the thread is unspooling at is precisely related to the rate that the spool has to rotate at, right? Imagine that the spool makes one full rotation. That means that it's let go of 2 pi r units of thread. The object will have fallen 2 pi r units. And so we can make that same relationship that relationship is precisely the non-slip condition. And this is just saying that the thread doesn't slip off of the spool. This is kind of just the reverse of the standard non-slip, where the round thing is the thing doing the moving. In this case, it's the ground, the thing that the round thing is on, that's doing the moving. It's the thread. So let's do energy conservation like normal. KEI plus PEI equals KEF plus PEF. So I'm actually going to do this one explicitly. So the initial kinetic energy is 0. The initial potential energy, let's just call this, let's call this coordinate. Let's call this position y equals 0. And then we'll call then this would be y equals minus h. Just so you can see how it works. So the potential energy there would be 0 because it's mg times y. Y is 0, then it's 0. And then the kinetic energy, so we have 0, which is equal to 1/2 times, well, there's a few things. Well, I will actually just write. Yeah, the kinetic energy would be 1/2 times the mass of the small block times its speed squared, plus the rotational kinetic energy of the spool, omega squared. And then we would have plus the potential energy, which would be, which would be mg times minus h. And so you can see why the h gets added up to the other side. So what we're left with is mgh equals 1/2 mv squared plus 1/2 I spool omega squared. So we can use the non-slip condition and the fact that this is a solid, let me just make an aside. The spool is a solid cylinder. So the moment of inertia of the spool is 1/2 mr squared. That's what I said earlier. It's in principle, it's something that you can calculate, but it requires a double integral. So I'm not going to make you actually do that calculation. Just trust me on this one. And if you don't trust me, go look up how to do it yourself. It's not too hard. And the non-slip condition tells us that we have, as normal, V equals R omega. Okay, so what are we left with? We're left with mgh is equal to 1/2 mv squared plus 1/2 times 1/2 mr squared. That's the moment of inertia of the spool times v over r quantity squared. Simplifying, we get 1/2 m plus 1/2 capital M v squared, which is just 1/4 times 2m plus capital M v squared. And so we can just, again, we can just solve v then is equal to the square root of 4 mgh over 2 times little m plus capital M. That just is the speed. Now, again, like I mentioned, no, in general, I'll give them to you. Or maybe you should just like write them. So any exam that you take is going to be open note. So maybe just write them down like a note card and then you can just refer back to it. But I'll probably give them to you. I'll let you know in advance. But so the important point is that the mass of the pulley matters. This is like a pulley, by the way. It's just a pulley with thread on one side rather than two, but you can imagine that it's the exact same thing. If we have a larger spool, if the mass of the spool is larger, that means that we have a smaller falling speed. So you can see that the reason why we made this massless pulley assumption earlier in the quarter was because if you don't assume that, then you have to account for the rotational kinetic energy of the rotating pulley. And that like if the mass is non-zero, then it matters. By the way, if you were extra curious, you could see what happens when the I want to make sure that I'm not lying to you. You would see what happens if the mass of the pulley is 0. Then it would just give you the result that you expected to get, which is just square root of 2 GH, right? just is the speed that you would get for a normal thing falling, because it doesn't take any extra energy to spin up a massless pulley. Anyway, so massive pulleys are now at least you've seen that you should have the tools to be able to understand problems that have massive pulleys. There's one last thing that we have to talk about now that we are allowed to talk, now that we have the tools to understand massive pulleys. If a pulley has mass, how does that affect the transmission of tension? So when we were talking about ropes and pulleys and so on, we had this understanding that the tension on one side was equal to the tension on the other side. And if the pulley is massless, that's just true. But if the pulley is not massless, that's not an assumption that we should fairly make. We should check and make sure that that's still the case. So let me work out an example, or show you an example. So we have our pulley. This is the standard block attached to pulley, attached to falling block type of thing that we've worked out a whole bunch of times. M2, M1. Sorry, it's not perfectly lined up. Initially, the speed is 0, and then we let them go. And importantly, the rotational velocity is initially 0. And we're going to assume that this pulley has a moment of inertia I. It just is what it is. Now, afterwards, I'm going to try to draw. It's similar, but not identical. Afterwards, after a block has fallen such and such a distance, everything's moving, right? Why does that keep happening? Those things are moving with, those blocks are moving with some speed v. This pulley is now rotating with the speed omega, assuming that, again, the pulley has a no slip condition, so the rope's not sliding over the pulley. Omega is related to v. The block has fallen some distance x, which means that this block has traveled some distance x. Right, this is all standard stuff. So now what we're going to do is we're going to apply the work energy theorem to the blocks. And we're going to use the original work energy theorem, which is the work done on an object is equal to the change in its kinetic energy. This is the one without potential energy involved anywhere. So the work done on block 1 is equal to the change in kinetic energy of that block. And so we can compute the work done on block 1. So the only force that's present on the first block is tension pulling it to the right. So I'm going to call the magnitude of that tension force T1, and the distance it travels, so it's force dotted into distance because the forces are constant. Sorry, because the forces are constant and the force points in the same direction as the motion, then the work is just the force times the distance, the magnitude of the force times the distance. So the work done is T1 times x, where x is that distance, and that should be equal to the change in kinetic energy. The final kinetic energy is 1/2 m1v squared. The initial kinetic energy is 0, so the change is 1/2 m1v squared. Now the work on the second block is similar, but there's now two forces. There's gravity and there's tension. Tension pulls it up, gravity pushes it down. So the work here is m2g. That's the gravitational force pulling it down. Remember, we're dotting it into the direction of motion, and the direction of motion is down, minus T2, where T2 is the force up, times the distance traveled equals 1/2 m2v squared. And so what we can obtain from that equation is that T2x, the tension, is just, we can just rearrange this and get that T2x, T2 times x, is m2 times gx, minus 1/2 m2v squared. All right, now this seems like we're kind of just not going anywhere yet. But remember, we initially were asking, how does a massive pulley affect the transmission of tension? So when we talked about the transmission of tension, in the past, when the pulley was massless, we assumed the tension on block 1 was the same as the tension on block 2. And that was a fair assumption because there was no extra energy going, or no extra energy or extra force going anywhere. However, we now we might not be so certain because there's another object in our system at play. So if we want to compare the tensions on the two objects, we would just subtract them, right? If T1 and T2 really are the same, then the difference should be 0, right? So T1 minus T2 should be, or is equal to, according to the calculation we just did, divide through by x, 1 over x times 1/2 m1 v squared minus mgx plus 1/2 m2 v squared, right? Now the important point is that this is equal to 1 over x. We can use what we know about the kinetic energy of our blocks to rewrite this. These two terms together give us the total change in kinetic energy of the blocks. So this would be delta KE blocks. And we know that the potential energy, oh, this should be an M2, sorry. The potential energy of our blocks go down because of gravity. So this term here, this is the change in potential energy of the blocks. So this here, this term, the change in potential energy of the blocks plus the change in kinetic energy of the blocks, this is 0 if and only if this is the change in mechanical energy. So if those two terms combined are the total change in mechanical energy of the whole system, then this is 0 because the whole system should have mechanical energy conservation. There's no external forces to the combined system, and there's no friction. However, the total change of the mechanical energy of the system is equal to the change of potential energy of the system plus the change of kinetic energy of the system of the blocks, plus an important point that we left out, the change in kinetic energy of the pulley. Because the pulley has mass, there is rotational kinetic energy associated with its rotation. And this term here, this is equal to 1/2 I omega squared, and that's not 0 if the mass of the pulley is not 0. And that's the important point here. So what we find is that T1 minus T2, this is equal to 1 divided by x times the change in mechanical energy, which we know is 0, minus the change in the pulley's kinetic energy. So this is 0. And so in particular, the change in the pulley's kinetic energy, this is positive because it started off at rest and it ended up rotating. And so the final kinetic energy for the pulley was larger than the initial kinetic energy for the pulley. And so what we have is that T1 minus T2 is less than 0 because there's a negative sign here. Or in particular, that T1 is less than T2. So when the pulley has mass, the tension force that this block M1 would feel is less than the tension force that this block would feel. And the reason for that is you can think of it kind of as like the source of the tension force is the gravitational force downwards on block 2, right? And so that tension force has two jobs. One of those jobs is to pull block 1. The other job is to get the pulley spinning. So that force is kind of split up between those two parts. Some of that force goes towards rotating the pulley. The other part goes towards speeding up the block M1. So it would make sense that block M1 would feel less of the total or less of the tension force than block 2 would. Now, there is one thing to mention. In this example, we really only computed the work done on the blocks. Right? And so we use the work done on the blocks to compute or to relate it to the kinetic energy of our system. But the change in kinetic energy of the pulley is not 0. So that means that there should be some associated work done on the pulley. So in order to answer this question, we need to introduce, or we need to incorporate force somehow into rotational motion. And I'm going to end it right there. This is exactly where I wanted to end up. This is going to take us into discussions of torque. Stop being frozen in a moment, so that way then I can end the lecture. And then I have office hours in a few minutes anyway. Come on. There we go. All right, so I'm going to end the lecture here, or I'm going to end the recording anyway. Oh, it froze again. Come on. Sorry for the technical difficulties, but at least we got through lecture without any of them today. I'm just going to unplug my webcam, see what happens. Ah, there we go.